believe in yourself, for that's the place to start. And I say, hey, hey, what a wonderful kind of day, if we can learn to work.
Hey fans, you're the fan, and I'm Ramin. Alright, so in today's video, we are going to talk about kind of what I said in last video, quantum entanglement, right? And really we're going to give some historical perspective before we go directly into it. It's a very interesting concept, and it ties into what we were talking about yesterday. So some of the people who have done like some reading some popular literature, you'll know one of these scientists very well, right? And just like yesterday, I don't really want to talk too much about the mathematical justification for this stuff because it's there. It's there. It's not very easy to understand if you don't know the linear algebra of it, and all that junk. But if you do, it's not too hard to understand, right? But math isn't really scary, so who cares, right? But we're gonna give some history on entanglement today, and like I said, it's funny because the reason why this concept even got brought up, excuse me, in the first place, is by these three scientists called Einstein, which you probably know, Polodesky, and Rosen. And the reason why they kind of brought out this experiment is because they really wanted to showcase that quantum stuff wasn't a complete description of reality. And the reason for this is because at this time, right, this paper came out in about 1935, right? And so, like I said yesterday, the spin experiment, the Stern-Gerlach experiment, came out in like 1927, and we had like Heisenberg stuff early on. We had Pauli stuff, Dirac stuff, Schrodinger stuff, right? So we're really in the midst of the quantum revolution at this point, right? This quantum logic is not only taking over, but it's becoming more mathematically defined. The experiments are showing that your predictions are correct. And really, we're in the revolution, right? The quantum logic is taking over all those paradoxes, and we'll have a video on those maybe a little bit deeper at some other time. All the paradoxes from the classical realm are disappearing. We're having explanations for them and predicting new things, right? So we're really in the midst of the quantum revolution at this point, which is about 1935. So, like I said, what they wanted to show was kind of like a gotcha. Like, I knew your quantum theories just weren't the real description of reality, right? They really did not like it that every single time these particles, these quantum objects interacted with something, there was no definite value, right? And so what they wanted to show was that, no, you guys are wrong. You guys are completely wrong. There are things called elements of reality. And that's exactly what it sounds like. Reality exists and there's elements tied to it, right? And funny enough, it actually led to a quantum justification, right? So you probably have heard of this new concept called quantum computers. They use this concept in the computational part. And so we will probably talk about quantum computing in maybe like 2 or 3 videos from now, because tomorrow's video will be on the byproducts of today's videos, right? So we're going to explain what quantum entanglement is. And then a guy came around called John Bell. And John Bell has these Bell theorems and inequalities, which are reliant on this concept we're going to discuss today. So, of course, we have to discuss this concept first. So, we're going to set up their idea. And you might notice that on this paint, I have some lines, right? And the reason I have these lines is because it's very scuffed, right? So I'm doing a screen recorder, and I have to know where to write some stuff. Okay, so the way the Einstein, Polodesky, and Rosen set up, which will be referred as EPR from now on, because I don't want to say their names every single time, is they started with a mass. Right? We'll call it mass right here, right? And it's unstable. And what that means is, and we can say molecule, you can say whatever, but the most important thing is it's unstable, so it's going to break apart, right? And the other thing that is important about this, it has 0 momentum. So let's pause here, right? Because we have to explain some physics lead up to this, right? And in this universe that we live in currently, right, we have some things that we just know are true because we have to assume that. One of those things is that the concept of momentum, right, is conserved. And what that means is, for example, think about a firecracker, think about throwing a ball. So like, me, I love throwing the ball concepts, right? You take a ball, you throw it. it's traveling, it has some momentum associated with it. Let's say the ball, for whatever reason, just starts to break apart, right? The momentum doesn't just die off and they get random components of momentum, right? In our classical world, the momentum is conserved, right? So the sum of all the break aparts, if you took all of their individual momentums, it would add up to the original ball. So that's why it's important to understand that momentum is conserved. So you have to know that first, right? And so in their thought experiment, right, this unstable ball, right, breaks apart, right? So and to keep it easy, they just say breaks off evenly, right? So it breaks off in two particles exactly, right? One goes off in some direction, the other goes off in some direction. And according to the quantum world, we don't know where they break off. We just know they do break off, right? So we know one thing currently. Momentum is conserved, right? So that's all you need to know right now. And then we have some guy over here. We'll call him Bob, right? And if you know physics, is that we love using two names, Bob and Alice, right? And so Bob is a scientist, so we'll give him, some like little nerdy stuff, like ooh. Okay, he looks like a nerd. He looks like me. And so Bob measures the momentum of the first particle. He says, cool, I get this random measurement, right? And so because we know momentum is conserved and we know that the particle or the unstable mass was zero momentum, we know the other particle that went off in this direction. So we'll do this one red and we'll do this one blue, right? So he measures this guy, right? He's like, oh, do. And remember, we're not saying anything about position yet, right? We're just doing momentum. And he says, I said this momentum is X for whatever reason, right? We'll just make it easier on our life. We know immediately, because of the conservation of momentum, this particle is immediately negative X momentum. Great, right? And so now, this ties into yesterday's video, and we will do another experiment involving exactly electron spin, right? But we're going to set up their experiment first, right? And so then you say, you know what, Bob? Not only are you going to measure the momentum, you then measure the position. So he measures the position, and he gets some value, we'll call it y, right? And so this is a concept known as Heisenberg's uncertainty principle, right? We're not so much concerned that he can do that, right? Because now we know, okay, we don't know the momentum anymore, right? Because according to Heisenberg, which is well established at this point, we know that his position measurement goes away. His momentum measurement goes away, right? We no longer know how fast this particle is traveling, but we do know its position, right? But guess what? Now that we know this guy's exact position, we also know the other particle's position, because we measured this position, right? They're not correlated at all, right? The measurement of this particle, why would it have any effect on the measurement of the other one, right? But guess what? We know this guy's momentum, right? Because of our first measurement, and now we can also give it a position, right? So now we're saying, I didn't even touch the other particle, but due to the conservation of momentum, I know your momentum, and now I can also know your position, right? Wait a second. That goes exactly against Heisenberg's uncertainty principle. So these guys said, we got you, right? We got you fair and square, right? You told me there were no elements of reality. But it seems like there are, right? Simply due to this thought experiment. The thought experiments show that if I measure the momentum, I know immediately what the other momentum is going to be. But then you tell me that if I measure the position, right, I lose what the momentum is going to be. But these things are so far apart, why would a measurement with Bob over here affect what's going on with Alice's particle over here, right? So we'll call this Alice. She's also a nerd, right? Why would it go affect her? So not only do we know her particle's momentum, we also know its position. Its position is going to just be some distance plus, this distance, right? Because it's going off in the other direction. It'll just be a definite distance, right? You can do it, make it explicit as much as you want, but we came to a paradox. This is in essence what the EPR paradox was meant to show. It was meant to show that your quantum theory cannot be a complete description of reality, right? you're telling me that, oh, these interactions change these definite values and you can't know position and momentum at the same time and all this junk, right? So that is what the concept of entanglement will be used to fix, right? And it's not, and that's why it's funny, right? It's funny because they actually led the quantum world into a different direction that probably wouldn't have went there if Einstein wasn't so hell bent on saying that, as he famously say, God doesn't play dice, right? If he could have just accepted the probabilistic nature of reality, quantum entanglement would probably get discovered, but it wouldn't have been as fast, right? Probably, probably someone else, like later on, would have seen these properties arise, and they're not hard to see arise, but it would have been a while. So that's in essence is how to resolve this paradox, right? And so I don't want to deal with their original experiment. We're going to deal with someone else's experiment by the name of David Bohm, okay? And David Bohm, when we talk about the interpretation video, he's also a very, very, very funny guy. So I don't want to talk too much about it now. I'll give you guys a little preacher to it. David Bohm did the same experiment, but he did it with spin. And that's why we're going to spend more time and we're going to resolve the paradox and we're going to explain explicitly what entanglement is using spin that we talked about yesterday. And so David Bohm, he set this up using spin. And the cool thing about David Bohm is he actually has his own, completely his own, it's very unique. It's called Bohemian mechanics. And Bohemian mechanics is a causal theory of the quantum realm. So he also didn't like the probabilistic stuff. And I mean, I'm not an expert on it, so I have to study a little bit before I do the interpretation video. That's why it's going to take a few videos to get there. But essentially, it's about how matter waves interact with particles, complex stuff. But he did the same experiment with spin. And so we're going to have to talk a little bit about spin in a different way. So how do we bring up this concept of spin involving this, right? So we know from yesterday that if I measure spin on the z-axis, I don't know spin on the x-axis, right? So knowing spin on the z-axis does not mean anything for my x-axis. You remember that from yesterday, right? The other thing I didn't talk about yesterday is let's talk about the actual measurements that you would see in the lab, right? So we're talking, oh, I could spin up and spin down. What does that exactly mean? So I'm just going to show you here real fast. If you get a measurement of spin up in the lab, you would get an energy value of h bar over 2. So this is for spin up. And probably if you're an astute student or if you're not, it doesn't matter, right? You can maybe guess, what do you think spin down is going to be? Right? Oh, it's just negative h bar over 2, right? So these are what you would see. These are the values you would measure in a lab corresponding to spin up and spin down, right? This is the same. So for example, if you measure on the z-axis, the x-axis, the y-axis, these are the values you will get in a lab, okay? And so we're going to set up the same experiment. Now, another thing I did not talk about yesterday, which I will talk about today, is what is spin? If you talk to the average physicist, right, and I'm not average, right, I'm a below average physicist, but if you talk to the average physicist, they will simply tell you that, oh, spin shows that angular momentum is quantized. And what does a quantized mean? Is because it has discrete values, right? And so that's what they would say. They would say, cool, spin shows that angular momentum is quantized. It's discrete, right? And it's conserved. Remember, the concept of momentum is conserved, whether it be angular, linear, whatever you want to call it, it's conserved, right? So we're going to do the same thing. We're going to do the same exact experiment, but we're going to use spin. So we start with some particle, some thing that decomposes, right? It decomposes and it has an angular momentum of 0 to start. And maybe, and if I was just about to write a 0 here, but maybe, maybe I should use actual letters here, right? So I'm going to write it out 0, right? So at 0 angular momentum. Cool. And so in order to evolve the system, we say this thing decays, right? It decays into 2 particles and they go off into different trajectories. So we're going to denote one with red. So we'll say this one goes off in this direction, and we go, and then we'll do this one in blue, and it goes off in a different direction, right? And so here we are, right? We have 2 particles. We know we know because of the conservation of angular momentum that once I measure one of them, I will instantly know the spin of the other one, right? And that will be the concept of tomorrow's video. We'll get there a little bit. But anyway, so we know this is going to happen, and so let's say hypothetically we have, let's get Bob out again, right? So Bob comes out, he's like, I'm a scientist, I love my experimental setups, and his head's a little bit off, but that's fine, right? And Bob measures this guy on the z-axis, right? And Bob's like, cool, I get a measurement of h bar over 2, right? And so what does that mean, everyone? It means he got a spin up, right? He measured spin up. So we know on the z-axis immediately, this guy is negative h bar over 2. Why? Because the sum, or when I add the two momentums together, it has to get back 0, right? So that's just how it goes, right? And so Bob then says, hey, you know what? I'm a little smarty. Not only can I have the experimental setup to measure this particle and on the z-axis, guess what, guys? I'm such a good experimentalist, I can measure it on the x-axis. And let's say Bob got negative h bar over 2, right? Okay. Well, guess what? We know that angular momentum is quantized, and we know that it's conserved, right? So we know immediately on the x-axis, this guy must be h bar over 2. And here's the paradox once again, right? We didn't do any measurement on the second one at all. But it seems like we have a definite value. We have some elements of reality. Not only do I know the z value, but I know the x value. Uh-oh, quantum mechanics is in trouble. However, you resolve this paradox with the concept of entanglement, right? We only say that the momentums are entangled with each other on that axis. So what does that mean, right? Let's go back to that concept. Remember, interaction changes values, right? What the Copenhagen's would call it is it's a collapse, quote unquote. You don't have to call it collapse, but that's just like what the popular nomenclature for it is. It's collapse, right? And there's some physicists out there that wouldn't call it collapse, but you should, right? So you collapse information. And so the paradox is resolved, right? You just say, okay, only these guys are entangled, right? And so these guys are also entangled, right? But what happens is because I made a measurement on the x-axis, this one's not known anymore, so this one's also not known anymore. Does that make sense? They're entangled together. They're dependent on each other, right? So Bob could go ahead, and just like we saw yesterday, Bob can go ahead and go back to the z-axis, and he could get negative h bar over 2. That does tell me that this one has to be h bar over 2 now, right? You see how I can switch like that, right? So that's how the paradox is resolved. Only the values on those axes are entangled, right? A measurement on one doesn't affect the measurement on the other one, but the values are still entangled, right? We didn't do anything with the second particle, but we knew it had certain values. Okay, this comes to another paradox, right? So for now, entanglement saves the day. Entanglement saved the day, right? It said, okay, cool. You measure that first particle and tells me the values of the second particle, right? But by measuring it again, you changed the value of the first one, so you don't know the value of the second one because the first one is unknown again, right? That is the resolution of this paradox that Einstein, Polodesky, and Rosen set up. And unfortunately, they did not win, right? Unfortunately, this is how reality works. Entanglement has been confirmed to work over and over and over. The measurement of one changes the previous value. So because it changed your previous value, the other value is also not definite. Because if I were to remeasure on the z-axis, I could get a different value. So I could get a spin down on the z-axis again, right? If I got spin down on the z-axis, then the other one has to be spin up, so it's not definite. Paradox resolved. Or so we thought. This comes into another thing, right? Some of you may know at this point, and it's fine if you don't. I'll give a better introduction to it tomorrow. But it's almost as if, because remember, we're not even talking about distance at this point. And this stuff has been confirmed up to like certain distances. I think like right now, entanglement has been shown to be working for up to like 11 kilometers, right? So what that means is if I measure this particle over here and then I measure this particle spin over here, and the distance between the measurements is like 11 kilometers, it works, right? So that's pretty big for particles, for given how small they are. Okay. Now we run into another conundrum. Are we or is information traveling faster than the speed of light? And that's forbidden by relativity, right? So it's almost as if we're saying, distance doesn't matter, right? These particles, they came from the same system, they are entangled in these ways because they come from the same system. We say momentum is conserved, therefore they have values that are, correlated to each other. They're entangled. That's what you want to say now. But doesn't that say that if I know this one to be spin up, then I instantly know this one to be spin down, and somehow information traveled faster than the speed of light here? I'll save that paradox for tomorrow, in which we will talk about John Bell's ideas involving Bell's theorems and Bell's inequalities. The reason why we use spin here, why I wanted to resolve the paradox using spin, is not only because I talked about it in yesterday's video, but also because John Bell used spin to derive and use these concepts for his inequalities, in which you will see that we can resolve that speed of light paradox as well. So let's just recap what we learned here today, right? We saw that these smart physicists that couldn't really handle this probabilistic reality of nature wanted to find a paradox in which, hey, you told me you can't know certain things while knowing other certain things. We resolved the paradox using entanglement, right? Which is, yeah, sure, you can tell me on that axis, you know what the momentum is of both particles, right? But as soon as I measure this one on a different axis, it changes its previous value. So this one becomes undefinite again. It's not known, right? Because measurement changes values. And that's all it is. That is all entanglement really is. It sounds cooler than it is sometimes, but it really is a very wonky thing, right? It's a very wonky thing, right? Because we're not even measuring the other particle, right? But somehow we know information about it because of how it's constrained in this system. So, like I said, that's probably a good place to stop. I probably did overtalk just a little bit, but I really want to drive home that point, right? Because it's a very wonky point, right? Measurement changes information, right? It changes values, right? And that's the point you want to go home. Quantum reality, quantum logic, right? It's very weird because, we like to say it's weird, but if you think about it, we're the weird ones, right? Our classical logic is a weird one. There's more particles than us, and those particles behave off of quantum logic, right? So even though it's weird for us, most of the universe is this logic. With that being said, tomorrow we will talk about Bell's inequalities, Bell's theorems. Hey, is things traveling faster than the speed of light? Is information beating that? Is relativity wrong? And so we'll give a little precursor to that tomorrow. With that being said, hopefully you enjoyed the video, and I will see you guys tomorrow.